So for the last part of the sample exam review for exam 3, we considered the final two long problems. So this long problem has a rod pivoted about a pivot at a certain point, and then the rod also is non-uniform. Its non-uniformity is described by this lambda function, which is a function of x. Now mind you, the direction x is down, so they've called this the x direction. The top end, the total rod is 4 meters, and it's 1 meter from the top end, so that's going to be x equals -1, and that's going to be x equals +3. So what you would have to do is integrate to find the moment of inertia. So that's similar to one of the problems we did before. That's going to be your mass element dm, and its width is going to be dx, and its location from the pivot is going to be this distance x. So our first step is to find the moment of inertia about the pivot, I sub p. What's that going to be? The moment of inertia is, by definition, the integral of r squared dm. That's the formula you will find in your formula sheet. Now the lambda function is defined as the rate of change of mass with respect to the coordinate, in this case the coordinate is x, and that's given as 3 plus 15 x squared. So from that I can solve for dm. It's 3 plus 15 x squared dx. And then I can substitute it in here. Now the value for r in this case is the same as x. So r equals x, and I'm going to get, there's not enough space here, so that's -1 to 3 times, I'll take the 3 outside because it's just a common factor here. So it's 3 times x squared times 1 plus 5x squared dx. This can be integrated. I can take the 3 outside. When I integrate it, I'm going to get x cubed over 3. And here, there's already a 3 outside. I get 5x to the power 4, which is, when integrated, just x to the 5. Between the limits -1 and 3. So that's nice. So that's going to be 27 minus -1 cubed, which is -1, plus 3 times 3 to the power 5. 3 cubed is 27, 3 to the 4 is 81, 81 times 3 is 243, minus -1 to the power 5, which is again -1. So this is going to give me 28 plus 3 times 244, and that's going to be 760 kg meters squared. The next thing we need to do is calculate the angular velocity of the system after the putty sticks to it. So here the principle to use is the law of conservation of angular momentum. Observe that when the impact occurs, there's going to be a reaction force exerted by the pivot in this direction. So you cannot conserve anything else, like linear momentum cannot be conserved, for example. Also, in a collision, energy can never be conserved. So let's not even think about energy being conserved during the collision. The only principle we can possibly use is angular momentum conservation. That tells us the initial angular momentum about the pivot point is equal to the final angular momentum about the same pivot point. Now this putty is coming towards this, and the angle is going to be all different, but just before it strikes it, the angle is going to be 90 degrees. So let's look at the angular momentum just before it strikes it. So it's going to be r times p times sine 90. So that will be good to write. The p vector is just mv naught. The r vector would be this distance. That's the distance 3 meters. Okay, but I'll just call it, let me call it something. Call it distance d. So it's going to be mv naught times d times sine 90 degrees, and that's equal to the moment of inertia of this system, ip. I'll call it ip prime because now you have added the putty to it, times omega. Okay, that gives us omega. Now the only thing that needs to be found here is ip prime, so let's do that here. Ip prime is ip, what you had before, plus you have to add the moment of inertia of the putty. The putty now is a point mass because it's said to be small. So it sticks there, and the moment of inertia of a point mass is just m times d squared. Let's substitute these values. That's 760 plus 0.2 kg. The putty's mass is really small, which makes this I prime not much different than I. So if you, that's going to be 1.8 actually, so that's just 761.8 kg meter squared. It's very small change. So now we can calculate what omega is. Omega is just mv naught d divided by I sub p prime. So let's put all the values in. 0.2 kg v naught is 20 meters per second, d is 3 meters, and this is 761.8 kg meter squared. And I did this beforehand. It's a really small value. Now you can expect with this kind of a initial speed, it's not going to go up very much, and you'll be right. But we're not asked to find the final angle, where it says do not actually solve. They just want us to speak in words. So what's going to happen is this initial rotational velocity will cause the system to have a rotational kinetic energy, which is 1/2 ip prime omega squared, and that rotational kinetic energy will be completely transformed into the gravitational potential energy of the rod plus the gravitational potential energy of the putty. And that's how you can find the final resting position, or I should say the momentary resting position of the system, because the rod's going to swing by a certain amount, and we don't know where the center of mass of the rod is. It's going to be somewhere down here because it's nonlinear, and this one's going to have, so both of them are going to swing, and both of them are going to have separate potential energy changes. So excuse me, that's going to be H1, that's going to be H2, and they're both going to swing like that, and you can relate this finally to the height, these heights to the angle theta using geometry. Let's go to the next long problem. The last long problem is a statics problem combined with some rotational motion problem in part B. So the statics part you have to solve by using static equilibrium principles. I'm going to call the forces on the hinge the horizontal component and the vertical component. I'm just making up this direction. The glued mass I'll call little mg. The mass of the rod, which is uniform, I'll call capital Mg. And there's going to be a cable force, which I'll call the force of tension. And also you have all these distances, so I'll indicate all of them. That's L over 2, and then That's a mystery distance. We don't know where it is, so let's call that x. And this distance is given to us to be something. We'll just call it d. The conventions here: counterclockwise torques positive, clockwise torques negative. Let's call our x-axis and y-axis. So let's first do in problems like this, you can go ahead and do the sum of all the forces in the x direction equals 0 and sum of all the forces in the y direction equals 0, but it's always preferable to start with the torque equation, because oftentimes that's all you really need. Now, the principle behind finding rotational equilibrium in statics is to always choose the axis of rotation to pass through the point with the most number of unknown forces, and that is precisely the hinge. So the sum of all the torques about the hinge point P is equal to 0. The hinge forces F sub h and F sub v do not contribute to the torques because the distance is 0. They don't make any torque. But these forces do. So let's look at the torque by the gravity force. That's going to be the distance times the force times the sine of the angle between the two, which is 90 degrees. The same here. This distance times this force, sine of the angle. And these are going to be clockwise torques because R cross F is into the page, and that's negative. So let's write them down. That's negative capital mg L over 2 times sine 90, which I won't write, minus mg times x. What about tension? That's the only one remaining torque. Here you have R, which is the d value, times ft sine theta, which is the same as 65. So that's going to be a plus because that's R, d cross f, which is positive. And all that should be equal to 0. Notice this gives you x immediately. So we can simply solve for x. Let me do this by taking x to the other side and keeping everything to this side. So I get mgx is equal to ft d sine theta minus mg L over 2. And then all I have to do is divide both sides by mg. Now they want us to find the maximum value of x, which can be found by setting the maximum value of tension here. And that gives us a maximum value. So now it's just a matter of plugging all these numbers in. We are told that the maximum tension is 2016. That's a joke because this exam was written in 2016. D is 7 meters, and that's sine of 65 degrees. Minus capital M, which is 150 kg, times 9.8 meters per second squared, times L over 2. Well, L is 10 meters, so L over 2 is 5 meters, divided by the mass of the glued mass is what, 60 kg, times 9.8 meters per second squared. Now I already did this before I started the video, so that's 9.25 meters. Observe that's almost close to 10. So the attachment point of the wire, so this figure is kind of wrong. The way the figures are drawn is kind of wrong. The glued mass will end up being here. But figures don't mean much in physics. They are just an indication. So your final answer is always what you need to trust. Now they say the string breaks. If the string breaks, all you have here in this problem is this. You have a uniform rod and the glued mass. Okay, so we can still draw the forces. That's going to be at that x max location we found in the earlier problem. And that's the distance L over 2. So now the sum of torques about the pivot or the hinge will be equal to the moment of inertia about the pivot times alpha. That's what Newton's second law is. For the sum of the torques, all I have to do is remove that tension force because the cable has snapped. I'll just write down what I have there. So I have negative mg L over 2 minus mgx, I'll put x max, is equal to the moment of inertia of this. Well, the moment of inertia of a stick about one end is 1/3 ml squared. And that's the point mass. That's what they say. The fluid mass is a point mass. So that can be written as the moment of inertia of a point mass is just mx max squared times alpha. So now we have everything we need to find alpha. Alpha is just negative mg L over 2. I'll take the negative sign outside, plus mgx max divided by 1/3 ml squared plus mx max squared. So number stuffing time so that's going to be 150 kg. I'll take the g outside, so that's 5 meters plus little m is 60 kg, x max is 9.25 meters, and I've taken the g outside, so that's 9.8 meters per second squared divided by 1/3 capital M, which is 150 kg, L squared, plus little m, which is 60 kg, times x max squared, which is 9.25 meters squared. And I'm not going to do the math here. When you do the math, you'll end up getting 1.26 radians per second squared. The fact that it's negative is what we are looking for, because remember, the direction of torque is R cross F for both of these. So the direction of both these torques is into the page, which is why you have the minus sign, and that should be the same as the direction of alpha. The direction of alpha is clockwise or also into the page, and so at least the directions make sense. So that concludes the complete solution of the sample test for test 3.